Skin may be the largest organ in the body, but it's also one of the most talkative when it comes to revealing secrets about age. We already know that wrinkles, dryness, and pigmentation changes are visible signatures of time's passage, but what if we could go deeper, past the surface, and read the microscopic whispers of cellular senescence to determine someone's true biological age? That's the idea behind using senescent subtypes in the skin, particularly fibroblasts, as biomarkers. Unlike chronological age, which simply counts birthdays, biological age reflects how well your cells and tissues are holding up. And it turns out your skin might be holding a surprisingly precise clock, ticking away in senescent cell patterns, molecular scars, and structural shifts that machine learning is now beginning to decode. The skin is a uniquely accessible window into aging biology. You don't need a biopsy from deep organs or complex imaging scans to gather data, just a punch biopsy, or even a few dermal cells harvested non-invasively. Within that small sample lies a rich, three-dimensional map of fibroblast populations. These aren't just generic support cells that sit quietly under the epidermis. They come in a variety of flavors, each with their own gene expression profiles, SESB secretions, and cellular morphologies. Some fibroblast subtypes are specialized in producing extracellular matrix components like collagen and elastin, while others regulate immune responses or participate in wound repair. When these subtypes become senescent, they don't all turn into the same kind of zombie. Some turn pro-inflammatory. Others become matrix disrupting. A few may actually dampen nearby cellular stress. What matters most is the proportion, location, and activity of these subtypes, and how they shift over time. Recent research using single-cell RNA sequencing has begun to catalog these shifts in exquisite detail. In youthful skin, fibroblasts are diverse but balanced. With age, certain subtypes, especially those prone to producing pro-inflammatory SASB molecules like IL-6, MMP1, and GM-CSF, start to dominate. These inflammatory fibroblasts correlate not only with visible aging features such as thinning dermis and delayed wound healing, but also with systemic markers of biological age, like immune senescence and glycation end products. In essence, your skin becomes a kind of external organ scorecard, a localized version of what's happening throughout the body. Here's where machine learning comes in. By feeding high-resolution images, gene expression data, and clinical metrics into neural networks, researchers are now training AI models to identify skin aging signatures that correlate with biological age better than traditional tools. These models can detect subtle features, morphological changes in nuclei, clustering of SASB-rich cells, patterns of lipid peroxidation or mitochondrial stress that escape the human eye. In pilot studies, these AI-powered analyses of senescent fibroblast distributions have been able to predict not only skin age, but systemic outcomes like frailty, immune decline, or even cardiovascular risk. And unlike blood-based biomarkers, which may fluctuate wildly due to acute illness or recent exercise, skin-based metrics appear more stable. The dermis is constantly exposed to environmental insults, UV radiation, pollution, oxidative stress, and that history gets embedded in cellular behavior. It's like dendrochronology for your face. The rings are there, but instead of wood, they're built from cytokines, proteases, and lipid oxidation footprints. The longer the exposure and the weaker the repair response, the more skewed your senescent subtype landscape becomes. What's especially intriguing is the potential for longitudinal monitoring. Imagine visiting a clinic every few years and having a skin scan that assesses not just collagen levels or hydration, but the precise state of your senescent fibroblast subtypes. Are you trending toward a higher inflammatory burden? Has your regenerative capacity dipped since last time? Is your skin acting biologically older than it should? Such insights could drive personalized anti-aging interventions, from topical xenotherapeutics to systemic lifestyle changes aimed at modulating senescence pathways. Of course, challenges remain. Not all skin regions age at the same rate. Sun-exposed areas show vastly different profiles than protected zones. There's also variability across ethnicities, genders, and lifestyles that needs to be accounted for in AI training datasets. And while fibroblasts are the main event, other skin cell types, like keratinocytes, melanocytes, and resident immune cells, also contribute to the aging landscape and may harbor senescent subtypes of their own. A truly robust skin-based aging clock would likely need to integrate multiple cell types, spatial transcriptomics, and perhaps even microbiome data to get the full picture. Still, the concept is gaining traction, and fast. Companies and research groups are already developing senescence-based diagnostics as part of cosmetic and medical dermatology. Some are even pairing these diagnostics with targeted senolytic creams or microneedle-delivered therapies aimed at selectively eliminating harmful fibroblast subtypes without disturbing the beneficial ones. It's precision aging medicine, starting at the surface but echoing throughout the body. In the end, the skin isn't just where we show age, it's where we can measure it. With the right tools, the right models, and a bit of help from AI, your skin's population of senescent fibroblasts might soon become your most accurate biological timekeeper. Forget the mirror. The real story of aging might be unfolding just beneath it.